The weakest of the forces are called dispersion forces. London dispersion forces, van der Waals forces. They all mean the same thing. So these dispersion forces are a weak, transient, attractive force between the molecules. So this occurs in all molecules, but is the predominant force or strongest force in nonpolar molecules. And what happens is that the electrons in the atoms are always moving around. And in the process of moving around, they'll create a partial charge separation for a very short duration of time, a partial charge separation. But when it does that, the adjacent molecule will reflect back the opposite charge, creating an attractive force. It's very transient, but it's there, and the bigger the molecule is, the bigger the cloud is, and the stronger this dispersion force becomes. So this dispersion force increases with molar mass of the molecule. It's the strongest force when we have a nonpolar molecule. It's always present in all molecules, and it increases as we increase the molar mass of the molecule. So, if we just change the size of the molecule, so we have three examples of hydrocarbons here. All hydrocarbons are nonpolar, so all three of these compounds are nonpolar. So we're going from a very small hydrocarbon, methane, to a medium-sized hydrocarbon, hexane, to a large-sized hydrocarbon, tetracosane. So the methane has a really low boiling point, melting point, and boiling point. It's a gas at room temperature. We call it natural gas. As we increase the size of the molecule, the melting point increases to minus 95. Boiling point increases to a positive 69. So it's now a liquid at room temperature. So by increasing the dispersion forces, the molar mass, we're increasing the attractive force that's holding it as a liquid and as a solid. Then we go up to a tetracosane, a 24 carbon molecule. This is a melting point at 51 degrees Celsius and boiling point of 391 degrees Celsius. A solid room temperature. So we're just increasing the mass of the molecule. We're increasing the dispersion force, the attractive dispersion force, and increasing the attractive force that holds it as a solid and as a liquid. Okay, this one, we haven't talked about ionic bonding. Ionic bonding is stronger than our covalent bonding. So ionic intermolecular forces holds ions together into solids or liquids. Ionic is a pure charge separation with positive ions and negative ions. The dipole-dipole is a partial charge separation, and that partial charge separation is attractive force. The ionic is an even stronger attractive force. Ionic compounds tend to be solids at room temperature. We have very few examples of ionic compounds that are liquid at room temperature. So here we can change a covalent compound, acetic acid. This is the active ingredient in vinegar. This has a hydrogen directly bonded onto oxygen, so this would be hydrogen bonding. If we react this with a basic compound, such as sodium bicarbonate, we can turn it into sodium acetate. This becomes an ionic compound now, sodium ion and the acetate ion. Or we can react with the potassium hydroxide to form potassium acetate, potassium ion and acetate ion. By turning it from a covalent hydrogen bonding into an ionic compound, makes a dramatic change in the melting point. We go from 17 degrees for acetic acid, so it would be liquid at room temperature, to over 300 degrees for sodium acetate, and about 306 degrees for potassium acetate. So turning it into an ionic compound makes it into a much stronger intermolecular force and turns it from a liquid into a solid compound. So another compound, we can do the same thing. Phenol has a hydroxyl group, so that's hydrogen bonding. If we react with sodium hydroxide, we can make sodium phenolate, which is an ionic compound. So the melting point goes from 41 degrees, a little bit above room temperature, to 382 degrees, well above room temperature. So ionic compounds, ionic is a stronger intermolecular force than hydrogen bonding, dipole-dipole, or dispersion forces. Amine, same thing. Amines are common in our proteins. We have amino acids. So amine is a nitrogen-containing group. So if we react that amine, which is basic, with a acid like hydrochloric acid, then we make an amine hydrochloride. It turns into a salt. We protonate the nitrogen, making it positive, and then we have the counterion chloride. But this turns it into an ionic compound, so the melting point jumps dramatically from minus 95 degrees Celsius up to 162 degrees Celsius. So we're going to identify intermolecular forces and then use that to be able to predict the relative levels of properties. So we're going to look at some properties that we can predict. One property is viscosity. Viscosity is the measure of the liquid's resistance to flow. So a high viscosity liquid will resist flow. It will flow slow. Think molasses or honey as high viscosity liquids. So you pour a jar of honey and it takes a while for the honey to start to come out of the jar. It's a very highly viscous fluid. Whereas a glass of water, you turn it over and it pours out immediately. So it has a low viscosity for water. So there are two things that will affect viscosity. The one thing that we're going to be using is just the intermolecular forces here. So the stronger the intermolecular forces, the more viscous the fluid will be. The other thing that will affect it is molecular complexity. So if the molecular is highly branched, it will become more viscous. We're not going to worry about that in this chapter. We're just going to worry about the intermolecular forces. So when we ask about viscosity, think about relative intermolecular forces. Is it hydrogen bonding? Is it dipole-dipole? Or is it dispersion forces? Another thing is solubility. So we mix two things together. They don't always dissolve in each other. So we can mix two liquids. Some liquids will dissolve completely in each other at any amount. Those would be miscible liquids. That would be alcohol and water, vinegar and water. Some liquids will not stay dissolved. Oil and vinegar will separate out. So for two things to dissolve in each other, we're going to be breaking the solvent-solvent interaction and the solute interaction and create a solvent-solute interaction. This solvent-solute interaction for a soluble compound should generally be on the same order of magnitude as a solute-solute, solvent-solvent, or stronger. If the solvent-solute interaction is too weak, the two materials will not be able to dissolve in each other. So in general, though, we're going to have polar solvents will dissolve polar solutes. Polar solvents, which have a partial charge separation, will also dissolve ionic solutes. Not all of them, but a lot of them. And then nonpolar solvents will dissolve nonpolar solutes. We call this the like dissolves like rule. So two things will dissolve in each other if they are of similar polarity. So since polar resolve polar, nonpolar resolve nonpolar, and since polar is a partial charge separation, ionic is a complete charge separation, ionic will tend to dissolve in polar but not nonpolar solvents. So two liquids that completely dissolve in each other are called miscible. Two liquids that will separate out are called immiscible. So oil and vinegar will separate out because the attractive force between the oil and the vinegar is really small, too small compared to the attractive force between the vinegar, and vinegar water. So the vinegar water is a hydrogen bonding attractive force that's breaking a strong hydrogen bonding to try to make a dispersion attractive force with the oil, and that's not favorable energetically. So for organic compounds, if we increase the length of the carbon chain, we are going to be making the compound more nonpolar. So this first one up here, we have butane, 4-carbon hydrogen, and we have octane, 8-carbon hydrogen. They are both nonpolar, so they are both insoluble in water. If we have a amine group, which is a nitrogen-containing group, amine has hydrogen bonding. That's hydrogen directly attached onto nitrogen. That's hydrogen bonding. So if the hydrocarbon chain is small, it will be soluble in water. As that hydrocarbon chain gets larger and larger, it eventually overwhelms the hydrogen bonding effect of the amine group, and it will end up becoming insoluble in water. Same for ketone. Ketone has a double bonded oxygen in the middle of a chain. So for acetone, it has 3 carbons plus that double bonded oxygen in the middle, and that is soluble in water. We increase that hydrocarbon chain up to a total of 7 carbons. We're increasing the hydrocarbon aspect. We're losing that dipole aspect from the double bonded oxygen, and it eventually becomes insoluble in water. Some more examples. Alcohols. Alcohols have a hydroxyl group, OH group. So this is a hydrogen bonding group. For small alcohols, they will be soluble in water. But as the chain gets longer, up to a 7-carbon chain here, it becomes insoluble in water. So carboxylic acid, this example is acetic acid. Carboxylic acid is a carbon, double-bonded oxygen with also a OH group on the same carbon. That makes this hydrogen a acidic hydrogen. It can come off in solution. Well, we know that acetic acid is soluble in water. We use that for vinegar. But as we increase that carbon chain up to a 6-carbon chain, it now becomes insoluble in water. So as we increase the carbon chain on these organic compounds, having oxygen or nitrogen on a compound tends to make it polar or even hydrogen bonding. But as we increase that carbon chain, it becomes more and more nonpolar.